Dr. M.
Yes, go ahead.
All right. Hey, everybody. We are Eric and Sandeep in Iceland, and our capstone was the Spatial Inference Project with the coordination with Meta and the Project Aria team. Uh, just going straight into the problem and motivation of what we're trying to do here. The future of XR and smart glasses is reliant entirely on the system actually understanding the user's physical world. This creates a massive bottleneck. When you try to capture the world, you are forming a continuous first person perspective, which we've keyed as a data fire hose. And then trying to continuously stream and run heavy AI models on 24/7 video is computationally impossible right now. If you're doing this on an edge device, it's going to instantly drain battery or overload power capability. You're going to choke up any sort of like bandwidth or any sort of like data transfer. And really, like 99% of what a camera is going to see in a given day is just going to be noise. So if we want to build a truly useful visual memory of someone's day, we can't process everything they see. The goal of this project was to solve that fire hose problem and build the foundational infrastructure for what we call an egocentric digital twin. It's a semantically searchable visual memory of the user's environment, completely stripped of the noise and perfectly ripe for some downstream spatial applications. Over to Sandy.
Oh, go ahead, Eric. Can you keep sharing?
Yep.
All right. So yeah, the functional requirements of our project here. There are two main requirements which are at the server end and the client end. So one of us is wearing the glasses, the other is basically reviewing what the glasses are seeing. So the first functional requirement is the gaze trigger capture on the headset, the second being the chatbot for object lookup on the client. Non-functional requirements, we are only focusing on the performance and the usability. So there are many non-functional qualities that we can be looking at, but only these two are important for our proper functioning of our project. So performance in real time requires that the live stream and the objects are basically detected and updated immediately. The scalability is we are limiting it only to one user. The maintainability, we used the code base using basically the modular architecture. Uh, Usability is also important. That is that only the gaze is supposed to trigger the function, nothing else. So there's no manual handling anywhere. So the next slide, please. So coming to the system architecture, we are splitting into the local and the cloud. So the local components, they're all right now in the Eric's home. So we are talking about two machines. So we are looking at a server machine and a client machine, the Aria glasses as well as the server contains a server is hosting a container with a image embedding model. So it's a vision transformer model. Uh, we are hosting it locally because it's quite expensive to like host it on the cloud. Otherwise, rest of the items that you see are the data structures and applications. So moving on to the cloud side of things, there is the Gemini 3.5 Flash, our everyday LLM. And then there's a text embedding model. It's a text encoder, Gemini embedding 2. Our main database, the Firestore, with two vector indices, one for image embedding and one for text embedding. And finally, the object store, the GCS, where we just store raw image files. So, okay, let's follow components by the data flow from the head to the tail. So, uh, right, the data ingestion starts at the Aria Gen 2 classes, which is fed to the server-side application through the Metas SDK. So that's where the gaze trigger calculations happen, and every capture that is ingested is added to the queue, which is on the RAM. So it's a ephemeral queue, and then that's where and the next step here. So far everything is being streamed. Everything after this is asynchronous and it's being handled by a separate thread. Uh, and here's where the enrichment takes place, the asynchronous enrichment. So we are capturing the image and the data, metadata. Uh, we are going to use the LLMs to add the object descriptions and the environment information. Alongside, we are going to use the text embedder and the vision transformer to create image embeddings and the text embeddings for our objects. So there might be multiple objects in single capture. So we're going to take that work, and that's going to be done asynchronously. So at the end of the streaming, the asynchronous work, we're going to store this in the Firestore, the NoSQL database, as well as we're going to store the images in the GCS. So this is basically the end of the pipeline. And we have basically created a semantic space for the objects of the image and the name. So we will have the object level, not image level, object level embeddings for images and their names that are generated by the LLMs. So this is the server end of things. So now coming to the chatbot, this is where the user queries using natural language about the object of interest. So the chatbot on the down. So chatbot is where two models interact. The generative model takes the chatbot's role, and it's responsible for passing the queries. So it's going to look up what objects the user is asking for and any other information, and it's going to pass it down to the text embedder. So text embedder converts the queries objects to embeddings to find the semantically closest matches in the database. And that is fed into a RAG pipeline, which is used to generate the appropriate query as the final answer to the client-side user. One thing to note is we are using the image encoder or the transformer for basically identifying duplicate objects and then associating them together. So that is part of the enrichment pipeline as well. So that's the role of the image encoder. And finally, the data viewer at the very bottom, that's just used for debugging tool, and we use it across different stages of development to just verify if our app is working or not. Next page, please. So there were four design choices that we had to ponder over. So there was cloud versus local at the very beginning. We originally had our Postgres database, but we had to migrate to cloud because we all were working on different data sets. So we wanted to have uh, one data set that with the latest runs. So that was the cloud migration was the choice that we had taken. There was the choice of LLM enrichment synchronously, but that would have basically bottlenecked the thread. And there was a lot of post-processing involved, with the image embeddings, and it would only allow for like one by one queue. Instead, if we used asynchronous, we could possibly parallelize it if necessary. Then there's the case of the third and fourth, which is basically using the vector database versus not using the vector database. We are using vector database to basically, we have images and we have the text. We're going to store them in a semantic space, and we're going to let the vector search basically connect both what the headset is looking at to what the user is basically asking on the client side. So passing on to Iclyn for the next slide.
Thank you. There are two main highlights of our project. The Aria headset's gaze tracking feature is key for intent-gated object detection, which forms the focus of our research objective. The Meta's SDK provides tools for tracking the deviation of the gaze, which allows us to identify objects of the interest where the user fixates on for at least 1 second. The k-nearest neighbor search feature of the vector indexes returns the closest objects with the semantic meaning within a set of distance of the queried image or the text. This allows the user to find the distinct objects of interest seen using the headset using natural language. Passing on to Eric for the demo.
Okay, so let's go ahead and tie all this together because there's a lot of moving parts here. Can everybody see the Project Aria chat box okay on the display? Cool.
Yeah.
Thanks for the thumbs up. So I guess kind of where I wanted to take this was like, okay, so I have this headset on my face that is kind of tracking what I'm doing or where I'm looking. It's capturing images based on like whether my gaze dwells on it for 1 second. What can that be used to do? And one of the first use cases we wanted to go for was like, hey, can it track objects persistently across real world space? Like if I'm have my keys and I'm just, walking around the house or the office or whatever and just putting the keys down on the table, picking them back up, can it track that object across like a persistent space and tell me the latest timestamp capture? So we can see here that it shows that, hey, the keys are currently in the bathroom, resting near the center of the vanity counter. The LLM is producing this enriched description from a forward image that we captured based on that glazed well pipeline and described. And then it went through kind of a matching pipeline. So we can see here that this is the same set of keys across two images. The matching pipeline actually just labeled the keys, cropped an image of them, performed both a semantic text description compare as well as an image compare, and correctly assigned this set of keys the same unique ID, so that between two separate captures, without having to fit it or prompt it too heavily, it identified the key, the same object across two distinct images within space, and basically allows us to do a timeline of the object throughout space. And so that's why when I say like, hey, where are my keys? It just takes the latest timestamped image where it captured the keys and just returns that. See, I kind of did the same thing with a pocket knife. This bounding box is like autonomously drawn. Gemini just kind of returns like an approximate bounding box for it. And, once again, says like, hey, yeah, you left it in the bathroom. Another use case we wanted to capture was something like, hey, what if, I have trouble remembering whether I took my medication, during the day. So because these images are time-stamped, we're actually able to do that. So the system basically captured that I was looking at my nasal spray, correctly labeled that object among many other objects within the frame. And then when I search for that object, using a vector lookup and a vector compare, it was able to say that like, hey, you last had your nasal spray, August 10th at 6:48 a.m. And so presumably I can now ask because I was wearing my glasses throughout the day, I can ask the system like, when did I last take my nasal spray? And it can just tell me when I did that, which is kind of like the opportunity that presents itself with this, first person egocentric digital twin. I kind of want to now show the pipeline capture in action. I'm gonna have to share the entire desktop. And so we have some pre-flight checks because I'm running the embedder out of my home server. All right, now the system is running. I'm basically just calling back my, approximate eye gaze vector coordinates. And now I'm gonna go ahead and dwell on something like my AirPods case. I'm also gonna dwell on this remote. And the reason that we wanted to set up this asynchronous process is like enrichment and analyzing of these images and then like sorting out the matching. All of this is very computationally intensive, and we didn't want this to go in the way of like capturing new images. So each time I make a capture, you can kind of see that it notifies that there's a capture here, and then it's going to tell me like once it successfully analyzes and posts into the Firestore database. So I'm just capturing a whole bunch of stuff. And then that AirPods case should have just populated right into the system. And here it is. Here's the room I'm in right now. And that's just kind of an end-to-end demonstration of exactly what we're doing. So I'm going to change the share settings here and pass it back to Iclyn.
Thank you, Eric. So some challenges we faced were we only had one set of Aria classes available for the project, which limits our testing of the server-side application by developers without them. Also limits the schema changes for the database pushed downstream to the client application. Object detection by the Gemini can miss cluttered objects. It is a common problem for models to miss objects meshing with the environment or out of focus to remain undetected. However, with the project on intent-gated objects being in focus, Dino version 2 requires GPU for real-time processing. Setting up a image embedding model requires a high-end virtual machine on the cloud that generates embeddings in real time. The solution was to set up a local container on a desktop rig with a GPU support. Hashing of the objects is still ambiguous. The current setup uses a static threshold of 15% for a cosine similarity of vector distance calculations based on Imperial's testing. This is not robust and generalizable for all cases, and the performance varies from model to model. User query parsing is still ambiguous. The text embeddings return semantic similar words from the database, but this is still model dependent and not perfect. Nor- Don Norm famously wrote about the difference between knowledge in the head and knowledge in the real world. He argued that human memory is frail and not a good and that good design places knowledge out in the world so we don't have to constantly rely on our own imperfect recall. With this project, we aim to build exactly that. We took the frail knowledge in the head, likely trying to remember where you left your keys or what time you took your medication, and externalize it. By demonstrating this intent gated architecture, we've presented a highly viable path to building a egocentric digital twin while maintaining hardware efficiency. The infrastructure is now in place. We took the messy physical world and made it naively queryable, paving the way for developers to build the next generation of spatial applications right on top of this foundation. Thank you.
Any questions? Any questions for this group? Okay. One question that I have is, I guess Sandeep was talking about the image encoder to detect duplicate images. And Eric, you were showing us 4 keys. What would happen if I ask for my car keys specifically?
Oh, as long as you've captured your car keys, then yeah, the latest timestamped image should show up.
So it can differentiate your door key from your car key.
I mean, we could certainly test for that. The embedding model that we used is kind of a rich combination of both the cropped image and the text description. And then by tuning the cosine similarity, we could,
What where,
see at what point they're.
where do you get the text description about the image?
The LLM is what performs during the initial
Oh,
raw frame ingest. Yeah,
okay.
it gets the text description.
One last question. How many images do you have in your database so far? Do you know?
Within the database right now, we have over 100 objects.
So what would happen if let's say we have 2 million objects in your database?
There would
So
be a massive scaling problem because k nearest neighbors is not perfectly optimally efficient. I think the way to scale this to hundreds and thousands and millions of objects would be to define some sort of boundary, probably a fine-tuned model, so that instead of doing like a compare with every other vector, we can simply just see if it lands inside of a boundary that we fine-tuned.
Okay. Okay. Sandeep, you have something to add?
yeah, we had like close to 100 images and close to 450 objects.
Okay. 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 Thank you. Thank you. Next group,